Moving on to the next organic question. So for nitromethylbenzene, which is that, so they have put that as position 1, 2, 3, 4. So you've got 4 nitromethylbenzene. You also form an isomer as a byproduct. Okay, draw the structure of this byproduct. You need to be very careful when you draw the isomer. The NO2 could be there, there. All right. But it's only an isomer of it, so there's only one nitro group. So you need to think about the CH3. It's an activating group. If you had a look in the data booklet, which you should know by the way, it's activating. It directs to 2, 4, and 6 position. Here it directs to 4. It could similarly direct to 2 or 6, all right? But it will just be one of them because it's just an isomer of it, so you just have one nitro group, could be there or there. But the thing is, it cannot be 3 because the CH3 is activating the 2, 4, and 6 due to the stabilization of the carbocation intermediate produced in that sense. Yeah. So this byproduct can only be 2-nitromethylbenzene. When you put the NO2 there, you want the lowest number, it will still be 1 and 2. Here is 1 and 2, so it will still be 2-nitromethylbenzene. All right. So you want to form this electrophile for the nitration. So you want to form that. So this is a classic first step in an electrophilic substitution mechanism. So you can watch a short tutorial video under the playlist A-Level Concept and Organic Chemistry. Look for electrophilic substitution. Inside that video, inside that short tutorial video, I outline exactly what kind of first step you're required before you jump onto the addition from the benzene ring itself. Yeah, that's to generate the electrophile. So between the HNO3 and the H2SO4, you will form the NO2 plus because that is what you want as your electrophile. The H2SO4 is the stronger acid, so you will become the conjugate base because it acts as the stronger acid. It also acts as a dehydrating agent, which means it will remove water, but you are still in very acidic environment. Your water will not survive just being water. Your water will protonate because you have so many H plus in solution. Your water will protonate and it becomes this trigonal pyramidal oxonium ion because now it has a plus with a lone pair remaining on the oxygen. So now there is a 107 degree because it looks like ammonia with 3 bond pair and 1 lone pair now. That equation is not balanced. If you leave that, then you are bound to get discredited. So you need 2 of the conjugate base to balance out the charge. And because you need 2 of that, you need 2 of the sulfuric acid. And that equation should be balanced now. You got 1 extra hydrogen from there, goes there. The 2H goes there. You have another 2H plus 1H, give you the 3H. The oxygen they come from the O there, and the SO4 are balanced, and then yeah, everything else is balanced. All right. So how does the structure and bonding, so they specifically bolded these two, of the 6-member ring, basically the benzene ring, differ from that in methylbenzene? In intermediate T. Okay. So how is this different from this? They are referring to this bit here, the 6-member ring. Okay. So compare about the benzene first, and you can hopefully see that this is no longer a carbon in the benzene ring. Well, it is a carbon in the benzene ring, but it's no longer aromatic because this carbon is now 1, 2, 3, 4. So this is the important carbon there, okay? Whereas here the carbon is only bonded to 1 hydrogen, all right? So in methylbenzene, we can say that all the 6 carbon in the ring are carbon sp2 hybridized. You should be very familiar with these terms called hybridization because they are part of structure and bonding in AS. So they are sp2 hybridized, trigonal planar, because they only have 3 bond pair each carbon, forming 3 each carbon, having 3 bond pair and 0 lone pair of electron. So essentially you just have like that. There's a CH3, you will have a very good overlap because each of the carbon will have an unhybridized p orbitals that allow you to overlap, therefore an aromatic system, meaning to say you get a full delocalization over the 6 carbon. Okay, so full delocalization of the pi electrons, okay, which is above and below the benzene ring itself, around the 6 carbon. Okay, but that's in methyl benzene. How does it differ in the intermediate? In T, so what happened now is you have CH3 and you have NO2, NOH, and then you have a plus somewhere. So essentially what you have now is you can delocalize this positive charge over the 5 carbon, but not here anymore, because here now you have a carbon sp3 hybridized. Okay, the carbon on which NO2 plus adds onto in the first step is now carbon sp3 hybrid dies. Therefore it's got 4 bond pair. As you can see, it's got a hydrogen, it's got NO2, it's got 2 carbon that is bonded to, 4 bond pair, and carbon has 4 outer shell electrons that it uses for bonding throughout here. Therefore tetrahedral 109 degree at that carbon. The rest of the carbon are still carbon sp2, therefore can delocalize the positive charge of the carbocation intermediate over the 5 carbon, but not over 6 carbon, because your 6 carbon is there. All right, so you lose the aromaticity around the 6 carbon. You can only delocalize it over what we call like this half smiley face, because it's not the whole 6 carbon atoms there. Okay, and you really want to go back to being aromatic, so you would lose the H. Okay, you would lose the H plus, and then you will get back the aromaticity. Okay, so hybridization, change in shape, talking about the aromatic versus the non-aromatic system, that's the kind of thing you can think about structure and bonding. All right, the bonding part refers, well, all of them are covalent, but the bonding part probably refers to the how many bond pair and how many lone pairs. So that kind of concepts are required in this kind of open-ended essay question. Very good question actually. Okay, so next bit is about benzocaine. So from step 1 to, in fact in step 1 you can see there is the bit there, so there's the reduction of the nitro group, and then this is an amide. So an amine can form an amide. You will need, however, a acyl chloride, and there will be a condensation reaction. When you form an amide, it's called a condensation reaction back in AS introductory organic chemistry. And here you oxidize so this is oxidation of the side chain of benzene. Okay, so this is specifically for side chain of the benzene. You can oxidize it to carboxylic acid. That's using your acidified MnO4 minus. Okay, and then here this is amide, and you're back to amine. So this is hydrolysis of amide. And to get to benzocaine, this is an ester. I hope you can see the ester. If you can never see the ester, always draw and show it. So start from the acid will lose the OH, and then the alcohol will lose the H, and then you condense these two together. So forming amide is the same as forming ester. It's also a condensation reaction. Now you want a systematic name for compound W. So it's got a phenylamine. And it's got a carboxylic acid as well. So you can think about this thing. This CO2H, this is called benzoic acid, when you have this NH2, that is called a phenylamine. So both of which are your A2's case study. Alright, so we can think about it being benzoic acid, and it's got a 1, 2, 3, 4. So it's a 4 amino, because when you have amine in front, it's called a prefix. You have to become amino. Alright. So reagent and condition for step 1, that is your thin and concentrated HCl to reduce your nitro group to amine, and obviously we need to reflux it to provide a little bit of kick. All right. Step 2, you need the ethanoyl chloride. It's got 2 carbon. It's an acyl chloride. It's called ethanoyl chloride. So I can write the formula. That is a lot easier. COCl. Because I'm using acyl chloride, I can do this at room temperature. Because acyl chloride is very reactive, I do not need to heat it or anything. All right. Step 3 is the oxidation. It's using the acidified KMnO4. You got to have the acidified, yeah. Of course, you can also use acidified MnO4 minus. All right, and you have to reflux it, otherwise it will not go. Step 4 is the hydrolysis of the amide. So we can use dilute HCl and reflux. Okay. Step 5 is condensation again. So I need the ethanol. I need CH3, CH2OH, because that is the alcohol that will require to give me the CH3, CH2O substituent there. And I need a little bit of corn sulfuric acid as your catalyst, so only a small amount. So better make sure that you write it as a catalyst, otherwise it will be implied it's a reagent, and we need to reflux it. Okay. So next bit is about the basicity of benzocaine versus ethylamine. So ethylamine is just straight chain amine, so 1 carbon, 2 carbon. Benzocaine is, well, benzocaine is, it's got an ester there. Okay, it's got NH2. This is still a phenylamine. So this is one of those fixed essay question, but instead of asking you compare 3 things, they just ask you to compare 2 things. We can talk that the benzocaine which contain phenylamine, containing phenylamine is less basic than ethylamine. We talk about the availability of the lone pair to donate to accept electron, right? So the inductive effect of electron donating alkyl group, okay, makes the lone pair on ethylamine more available to accept proton, whereas in phenylamine the lone pair on the nitrogen. So when you have a phenylamine system, it's best exemplified with a diagram. When you, of course, you will have the ester bit there, which doesn't matter. You have the NH2 bit there. So your lone pair actually can get delocalized into the ring. So lone pair of nitrogen in the phenylamines gets delocalized into the benzene ring. Okay, therefore less available to accept H+. So it's just not the trend, but it's also comparing the inductive effect versus the delocalization effect there. Yeah? How available are the lone pairs to accept proton? So next bit is about NMR. If you want to predict the number of peaks seen in the carbon-13 NMR for benzocaine, so this is benzocaine, it's a good thing I don't have to keep on referring up there. We want the difference in the number of carbons. I hope you can see there's a symmetry there. So this is a single bond. You can freely rotate about single bond. You can freely rotate about single bond. But that carbon is different from that carbon. That carbon is bonded to NH2. That carbon is bonded to the ester. This carbon is the same as that carbon because of the mirror plane, the symmetry there. This carbon that I've just drawn there is the same as that carbon there, okay? But this and this are different because there's no mirror plane there, because this side and this side are different. This side is closer to NH2, this side is closer to the ester, okay? So those are the different carbon in the ring. This is nitrogen, so there's no carbon. This is different, this is different, this is different. So altogether you have 1, 2, 3, 4, 5, 6, 7. So you will see 7 peaks in the carbon-13 NMR, okay? So now this is the proton NMR. Why do you use CdCl3? Why not CHCl3? Well, this is a solvent. If you use CHCl3, if CHCl3 is used, additional proton environment would be observed. Okay, so yeah, I mean, like if you use CdCl3, the deuterium is not NMR active, therefore won't be observed. So you don't want additional signal essentially in your NMR, okay? And then use the data booklet and the spectrum to complete the table for the NMR spectrum, right? So you get 4 different proton environment. What are the 4 different proton environment? I think it's best if I redraw benzocaine. CO, CH2, CH3, okay? So there's NH2 there. First of all, there is a proton there. Oops, maybe I use a different color. There's a proton there, there's a proton there, there's a proton there, there's a proton there, and proton there. So 1, 2, 3, 4, 5 environments, 5 proton environment that are different. This is the same as that, this is the same as that because of the mirror plane. This is proton, that was carbon, alright? You get, that is a 0, that is just a reference. That is usually your TMS, which is your tetramethyl silane. Oops, sorry, 4 of them. So it's 4 methyl on a silicon. So it's 0.0 as reference. You see this thing at very low region. So those are usually the CH2, CH3. This is a bit high because this is next to a carbonyl. So this is your, let's say this is your A, B, C, D, and E. Your C and D are close together because these are where the aromatic protons are. The aromatic proton means protons bonded to benzene ring. They are together there, okay? So all of these and all of that, they will be around this region. Which means this must be the NH2. So you can see they're a bit broad rather than sharp because of the labile proton. So we talk about labile NH or labile OH, they are both labile. They can undergo quick deuterium exchange with D2O, for example, yeah? So this has to be the CH2 next to a carbonyl. That has to be you because you see 3 proton next to you. That's why you get 4 lines because you have 3 neighboring proton. 3 plus 1 will give you 4 lines. They are a bit high in ppm because they are next to a carbonyl. Whereas this one is quite far down because you are here. When you are here, you see 2 neighboring proton. It gives you 2 plus 1, which is 3 lines, and you're not next to a carbonyl. And what else can I say? So there must be A, there must be B, this must be C and D, and there must be E. All right. So the group responsible for the peak, the 1.2 is CH3. CH3, maybe you just write the proper group. CH2, and then there's the NH2, there is the aromatic protons. Okay, so this is the CH2 next to carbonyl, just to be specific. That was this is a triplet, this is a quartet, this is a singlet, this is a multiplet. Okay, well, they already told you the multiplet, right? So what was that again? Triplet. A quartet, so make sure you can spell it properly. A quartet, Q-U-A-R-T-E-T. This was a singlet, but it was quite broad. There's 2 proton because there's 2 proton on the nitrogen. 2 proton there, 3 proton there. Aromatic proton, do not forget there are 4 of them altogether in this region, because this repeat with that, this is the same as that, but they overlap together in this aromatic region, usually between 7 to 8. So there are 4 of them. 3, 4, 5, 6, 7, 11. Work out your molecular formula of benzocaine. You see 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14. So I've done a mistake. What have I done? 3, 4, 5, 6, 7. So I think I was right. There is 11 protons altogether. So you will get 3, 4, 5, 6, 7, 8, 9, 10, 11. This is not a proton, that has oxygen. Okay. So explain the splitting pattern for the absorption at 1.2 ppm. As I mentioned earlier, we are looking at when you are here, the splitting pattern is a triplet. That means it's for CH3. So you say the CH3 sees 2 neighboring proton on the CH2. So the CH3 at 1.2 ppm sees or has 2 neighboring protons. That's on the CH2. Therefore, 2 plus 1 equal to 3 lines. That will give you 1:2:1 splitting of a triplet. That's why you see a triplet there. Alright. So when you dissolve in D2O, so that will get rid of the labile proton. So typically you always think of OH, but don't forget that labile proton can also be NH. And in benzocaine, as I mentioned earlier, you have a labile proton with the NH. So the NH labile protons of the NH2, the phenylamine, will undergo fast deuterium exchange with D2O. So once the NH2 becomes ND2, this will not be observed. Okay, this will not be observed in the proton NMR because, well, proton NMR detects proton 1, hydrogen 1. This is hydrogen 2. Okay, so how it works is basically when you have RNH2, you have D2O, they are in equilibrium. So this is potentially what could happen. When you get that, then there's no more hydrogen and nitrogen. This peak will disappear, alright, due to the fast deuterium exchange. So benzocaine can also be used to synthesize the dye stuff S. So you want to form a dye. We have to think about azo. And to form azo, we need diazonium. So the diazonium will react with alkaline phenol, so that to make that deprotonated and a much better nucleophile, you would need to convert that into a diazonium. That will give you N and N. So the nitrogen there is a sp hybridized because it's got 2 sigma bond and 2 bond pair therefore, and there is 0 lone pair, so it's a linear 180 degree. Don't forget that you do this diazonium with HONO, or sometimes you call it HNO2, and do HCO and 0 to 5 degrees Celsius because these are very heat sensitive. So you treat that with that, and what you're going to end up with is the ester group remains as the ester, which is the CO2, CH2, CH3. The diazonium become azo, and then this group is 2, 4, and 6 directing. Okay, but in terms of steric, I can imagine it going there instead of going any of these. All right, so my phenol would be like that, but don't forget that you need to show your phenol as well. So like I said, I most likely will go there, which is 1, 2, 3, 4 is directly para or position 4 to the phenol. So what we use in step 1, that is the diazotization of the phenylamine. So that's just using HNO2, which is the same as HONO. When you think about it, you just sum up the oxygen there. So HONO looks like this. That's why I always think of it as HONO, but it's actually HNO2. And then you need HCl. So those two are both aqueous. And you need to keep it cold at 0 to 5 degrees Celsius, right? So I already did for R and the S, and most importantly, you got to think about the position. I mean, one of the possible answer could be the one where you add onto the position 2, so that's perfectly feasible as well. Alkaline condition, a lot of students forget that because this is acidic. To make it into a better nucleophile, to further activate it, you make it into a phenoxide anion, alright?